Hey guys, in this video we're going to take a look at some practice problems related to the synthesis and reactions of amines from LTQ 9.1 in the spring 2024 semester. And in this first problem, we're just asked to predict the neutral organic product of each reaction. Now, from a very, very high level with amines, we want to keep in mind that the amino nitrogen is nucleophilic and basic. And we also want to keep in mind these ways we know of preparing amines, like reductive amination, reduction of alkyl azides, reduction of amides, and things even like electrophilic aromatic nitration and reduction of those nitrobenzenes as well. But for now, we're looking at a reaction of an amine, specifically a reaction of an aniline here, or aminobenzene, with sodium nitrite, NaNO2, and HCl in the first step. Now, NaNO2 and HCl combine to form nitrous acid, HONO, and under these reaction conditions, that HONO can get protonated and lose water to form the NO plus cation, which is known as the nitrosonium cation. And this is a fantastic electrophile that can engage with the nucleophilic amino nitrogen in primary and secondary amines. And if the amine is primary, meaning it only has one carbon group attached to the nitrogen, which is the case here, we end up with a diazonium. And so here specifically, we're going to end up with an aryl diazonium species in the reaction mixture. And this will be the primary fate of the aniline in the first step of this sequence of reactions. We're going to have this aryl diazonium, and notice that the methyl group that was present in the original substrate is still there. Now, what's the deal with the copper-1 bromide? Well, long story short, copper-1 bromide is a source of bromide as a nucleophile, and for mechanistic reasons, the copper-1 facilitates loss of N2+ as a leaving group, and the bromide can then substitute for the N2+ overall. So the net result here is going to be replacement of this great leaving group. Let's actually highlight that briefly, that this N2+ group is a fantastic leaving group and can be substituted by the bromide nucleophile. The mechanism here is not quite nucleophilic aromatic substitution, but you can think about it that way. And this is a great way to think about it, because this is going to lead us to the final product, which is the corresponding aryl bromide. So the net result here is substitution of the NH2 group for a bromine, and this general idea of substituting an NH2 group for a nucleophile typically involves an aryl diazonium intermediate in the use of HONO. All right, what's going on in the second case? Well, in the second case, we have this secondary alkyl iodide reacting with NaN3 sodium azide. DMF is dimethylformamide, that's just a solvent. And then we're doing some kind of reduction with lithium aluminum hydride, followed by aqueous workup. So let's take it one step at a time, as we usually do. Now, sodium azide, the Na plus cation, pretty much does nothing. And so we're thinking here about N3 minus as a nucleophile. This N3 minus nucleophile can displace the iodide, and here I'm being a little sloppy with how I'm drawing N3 minus, but this will save us a little bit of time. And this is an SN2 step, so this is going to occur with inversion of configuration. This is important for this problem since that carbon bearing the iodine is stereogenic. And so we would see an inversion of configuration predominantly in this first step. Now that we've got the N3 group connected there, if we draw out the N3 group, we're going to notice something, that we have a N2+ leaving group that's built into this thing. So the purpose of lithium aluminum hydride is essentially to shove off that N2+ leaving group and replace with H-, a hydrogen. So this creates a new NH bond, and after the aqueous workup, N2+ is going to be gone, and we're going to end up with two new hydrogens connected to the nitrogen. So we end up with a primary amine, and this general strategy of substituting, doing an SN2 substitution with an azide followed by reduction with LiAlH4 is a great way to make these primary amines with one alkyl group connected to the amino nitrogen. All right, in this third example, we again have a primary amine, and we're starting with an excess of methyl iodide. Methyl iodide is an alkyl halide, and we're familiar with this idea that the purpose in life of this reagent is really to supply an electrophilic methyl group, and the amino nitrogen is nucleophilic, so we can think about alkylating that amino nitrogen repeatedly and losing protons to get to a trimethylammonium species, something that looks like this. And if we stopped after step 1, this is where we would end up with iodide as a counterion. But the purpose of the second step is, first of all, to take that I- out of solution. Silver plus and I- form an insoluble precipitate in aqueous solutions. And OH- will be the result. And OH- is a decently good base, and so has the ability to deprotonate at a beta carbon relative to the trimethylammonium group. And here we're thinking about an elimination that's kind of like an acid-catalyzed dehydration that you may have seen in Organic Chemistry 1, where the OH- can deprotonate beta to this leaving group. We want to notice that now that that nitrogen is positively charged, it's potentially a good leaving group. Deprotonation beta to that leaving group can form an alkene. And the interesting and nice thing about these conditions is that this occurs at the less substituted position. Notice that this H is the less substituted beta hydrogen relative to the beta hydrogen here, due in part to the bulkiness of that trimethylammonium group. Elimination is going to occur selectively at that less substituted position, and we get the less substituted alkene. So this reaction, which is called Hofmann elimination, is a complement to the Zaitsev eliminations that you've seen previously. Finally here we have this aldehyde, benzyl aldehyde, we might say, or phenylacetaldehyde, reacting with diethylamine, so it's a secondary amine and acetic acid, followed by this reagent, which is sodium cyanoborohydride. We want to think of the Na plus cation and BH3Cn- as an anion in its own right. This is like BH4- in which one of the hydrogens in borohydride has been replaced with a cyano group. So it's a reducing agent, and the hydrogens that are built into the BH3Cn- anion are nucleophilic hydrogens. But that's getting ahead of ourselves a little bit. What's going to happen in the first stage of this reaction when we combine the aldehyde with a secondary amine and acetic acid? I do think it helps here to kind of step through this mechanism one step at a time. We have seen previously that secondary amines in the presence of an acid will react with ketones and aldehydes to form enamines, and this involves, for example, a carbonyl amine intermediate. So we can think about adding the diethylamine to the aldehyde, get something like this, and this can eliminate water with or without protonation. And I'm actually going to show the elimination of water with protonation of the oxygen, just to make a point about what happens in the reduction stage. We can eliminate this way to create a carbon-nitrogen double bond. We do this in imine formation, but here we can't lose a proton, so that nitrogen is sort of stuck with positive charge. We end up with a species like this. A number of people drew it without positive charge on the nitrogen, but that would violate the octet rule. Watch out for that. And this species is certainly going to be present more or less in this reaction solution thanks to the presence of acetic acid. Now, at the same time, the enamine will also be present, and this comes from losing a proton from the alpha carbon, losing a proton from this carbon right here, and then pushing electrons up to that positively charged nitrogen. There's some equilibrium between the enamine and this iminium ion. And this iminium ion can be reduced by the cyanoborohydride anion. That looks something like this. The boron is formally negatively charged, but we know that the hydrogen is really the nucleophilic bit in the borohydride anion. And so something like this is going to add a carbon to that, add a hydrogen rather to that former carbonyl carbon, and what we end up with at the end of the day is an amine. This iminium ion accepts hydride, and we end up with this amine. So this is an example of reductive amination. It's an amination reaction where we form a C-N double bond through iminium or imine formation, and then we reduce that C-N double bond to a C-N single bond and a new CH bond, essentially, using sodium cyanoborohydride, or in some cases, H2 and a metal like palladium or platinum. In this problem, we're asked to determine reaction conditions that accomplish each of these transformations. And in the first case, the first thing I think we should do is be very careful about numbering carbons. We've got 4 carbons in the substrate, but we have 5 carbons in the target. So our synthetic approach needs to add a carbon and an NH2 group to the starting alkyl bromide. A common but erroneous approach would be to do something like the azide and reduction approach that we saw above. If we used, for example, sodium azide, that would replace the Br group directly with an N3 azide group. And then reduction of that would give not pentylamine, but butylamine with only 4 carbons instead of 5. To add an extra carbon and a nitrogen, I think the easiest way to think about this, and there are multiple approaches, this is only one, multiple approaches, is to think about using cyanide as a source of carbon and nitrogen already linked together. So something like sodium cyanide in a polar aprotic solvent like DMF can do an SN2 substitution and put a cyano group where that bromine is located, and notice this cyano group supplies carbon 5 in the final product. And to get there, notice we need to reduce that CN triple bond group to a CH2 NH2, and lithium aluminum hydride is the perfect reagent for this, followed by aqueous workup to supply the protons we need to get a neutral product out of this. Great way to synthesize primary amines containing a CH2 NH2, and recognizing this additional carbon was absolutely key. In the second reaction here, we're supposed to transform aniline into this compound containing an N-N double bond. This is known as an azo compound because of the N-N linkage here. This is known as an azo linkage. And so we should think about Azo Coupling here, which is a reaction between an electrophilic aryl diazonium and a nucleophilic aromatic ring. Now, in order to get the connectivity we want, with a phenyl ring on one side and dimethylamine on the other side, it's important to notice that we're going to need to turn our starting aniline into the diazonium. Since what we want to happen here, we can sort of draw this over the arrow, we want this just benzene diazonium to be attacked by the nucleophilic dimethyl aniline. So let me do that in a different color. I'll do that in red. What we want to happen here is the dimethyl aniline to attack the benzene diazonium. And so we need to elaborate our starting aniline to this benzene diazonium, and then we're going to add the nucleophile in step 2. So I'm just going to move this down and put a 2 in front of it, since this is all we're going to need to do the azo coupling once we've got the benzene diazonium. And the only question left is, how do we make that benzene diazonium? Well, we've already seen how to do this. We can use nitrous acid. Let me do that in purple. We can use nitrous acid, HONO or HNO2. And the most common way that nitrous acid is generated practically is through the use of a nitrite salt, alkali metal nitrite, like sodium nitrite, and hydrochloric acid, which will protonate NO2 minus to make HNO2 in solution. So this is an example of azo coupling. It's a great way to establish this N-N double bond, and these products are often highly colored azo dyes, useful in a wide variety of applications. Finally, here we're tasked with drawing a mechanism for this reaction. And one thing we should notice here is that what we're dealing with on the reactant side is an acyl group connected to N3. This is known as an acyl azide. It's very similar to the alkyl azide that we drew earlier in this video. It just has an acyl group connected to the azide instead of an alkyl group. And this has some interesting consequences. So the reaction conditions are essentially we take this acyl azide, we dissolve it in ethanol, or we prepare it in ethanol, and then we just heat things up. And acyl azides have this capacity to rearrange. This is Important thing to know about acyl azides, because this is a highly convenient synthesis of amines. This is why we care about this. This N2 plus group is a good leaving group, and we've seen this in other contexts already. This group wants to do this, and that would leave the nitrogen neutral, and a number of folks actually drew the neutral nitrogen species, something like this, as part of their mechanism. This is actually not so crazy. And whether this species was involved in reactions of this type was hotly debated back in the day. Nowadays, it's become apparent that this is probably not how things work, but it's on the right track. Thinking of the N2 plus group as a good leaving group is the right idea. Instead of just a loss of the N2 plus group, though, what happens at the same time is rearrangement of this methyl group. If we back up for a second, one thing we should notice about the product in relation to the starting material is that this CH3 group that was connected to the carbonyl carbon is now linked to nitrogen. And this carbonyl group, this carbonyl carbon, appears to have lost its bond to the methyl group. So that bond is cleaved and a new carbon-nitrogen bond is formed. And this arrow right here, this curved arrow, is showing exactly this. There are other logical possibilities for breaking that bond. For example, we could think about breaking that bond this way or breaking that bond this way, but that's going to generate an anionic species that's highly unlikely under these pretty much neutral reaction conditions. So the rearrangement is the most plausible way to think about this, avoiding, for example, a CH3 minus anion. And where does this get us? Well, if we follow our logic, this gets us to a structure that looks like this, where we've made that nitrogen-methyl bond. The nitrogen is still negatively charged. If we do our charge math at this nitrogen, we've lost an electron, but also gained an electron, so the nitrogen is still anionic. And now this carbon is positively charged since it lost a bond. There's a resonance form of this where everything is neutral. And I'm going to go ahead and just draw that by taking a pair of electrons on this nitrogen and just forming a C-N double bond. And the geometry is a little bit off, but the C, N, and O here are all collinear. This is known as an isocyanate, and it's typical in these rearrangements of acyl azides. This isocyanate intermediate is key to the Curtius rearrangement, which is what we're dealing with here. Now, we haven't engaged the ethanol yet. A number of people thinking about that positively charged carbon or the fact that this carbonyl carbon is electrophilic added the ethanol before they thought about this rearrangement or loss of N2+. And this is in some ways good, in some ways not good. Not good in that the isocyanate intermediate is very typical of Curtius rearrangements, and addition of the ethanol to the starting acyl azide is probably less plausible than an initial rearrangement. But even so, addition of ethanol is where we're going with this. This is how we make this new bond between the ethanol oxygen and the carbonyl carbon. This kind of bond we've seen made through the addition of nucleophilic alcohols to carbonyl carbons in other contexts, right? And so we can think about now, okay, this carbon is still an electrophile. Now it's got two double bonds to heteroatoms instead of just one. We've got in our reaction mixture a nucleophilic ethanol molecule. Doesn't make sense to deprotonate this just yet. A number of people tried to transfer the proton of HOET, for example, to nitrogen in the isocyanate, and that's just a very disfavorable proton transfer. It's actually worth pausing the video and drawing that out to convince yourself that that is not the best proton transfer to invoke. But this nucleophilic addition is actually completely fine. I think it's most plausible actually to think about a Zwitter ionic intermediate here with positive and negative charges. So we'll have something like, well, let me redraw this so that it's starting to look like the product. We'll have the carbon-nitrogen double bond still intact. We'll have an O minus. We'll have an O plus. And the ET group there, something like this. And if you stare at this long enough, you'll probably realize, wait a minute, this just is the product. The only difference is this proton needs to be located at nitrogen instead of oxygen. So what we need to happen is a kind of tautomerization process where the proton is removed from that positively charged oxygen first and then put onto the nitrogen, which actually has some negative charge, right? There's a resonance form in which that nitrogen is negatively charged. And then we would get to the final product. So here I'm just going to abbreviate this as PT times 2. A couple of proton transfers would convert this structure into the final product, and the net result after the isocyanate is just the addition of ethanol to the isocyanate intermediate. When aqueous workup is used, the resulting structure that has an OH here instead of an OR group can lose carbon dioxide very easily and give us a primary amine. And that's sort of your classical Curtius reaction that converts an acyl azide into a primary amine.